right now, as you listen to this, you are hurtling through space at a speed that would make your head spin if you stopped to think about it. Not just around the sun, not just with the sun around the center of the Milky Way, but along with every galaxy within 500 million light-years of us. All of them sliding, like water flowing downhill, toward a gravitational valley so massive that astronomers simply call it the Great Attractor. You have never been still. You have never been stationary. And the place you are being pulled toward is part of a structure so staggeringly vast that it took humanity until the late 20th century to even realize it existed. A structure woven from invisible matter, sculpted by forces older than the stars themselves, and stretching across the entire observable universe like a net cast by something far beyond our comprehension. It is called the cosmic web, and it is, without exaggeration, the largest thing that exists. Think about that for a moment. Not the largest thing we have found, the largest thing there is, bigger than any galaxy, bigger than any supercluster, bigger than anything you have ever seen or ever will see with your own eyes. It connects everything. Every galaxy, every cluster, every void, every atom of hydrogen drifting between the stars is arranged according to its architecture. And the strangest part of all is this: the blueprint for this unfathomable structure was drawn less than a trillionth of a second after the universe began, when the entire observable cosmos was smaller than a grain of sand. To appreciate what the cosmic web is, try to imagine something that is truly difficult for a human mind to hold. Imagine taking every galaxy in the observable universe, all 2 trillion of them. Now imagine stretching them out along invisible threads of dark matter, connecting them in an enormous lattice of glowing filaments and yawning voids. A pattern that repeats and recurs across the entire sky, across tens of billions of light years, across the totality of everything that light has ever touched. That lattice is the cosmic web, and it is not just large. It is the frame upon which all of cosmic history hangs. Everything that has ever happened, every star that has ever burned, every planet that has ever cooled, every civilization that may have ever risen and fallen on some distant rocky world has happened within its architecture. This is the story of the cosmic web, how it was discovered, how it was built, and what it tells us about the deepest nature of reality. It is a story of patient gravity and invisible matter, of frozen sound waves and quantum seeds, of brilliant minds, accidental discoveries, and supercomputers that can simulate the birth of galaxies from scratch. It is the story of how the universe became the universe. But to begin, we need to do something that sounds deceptively simple. We need to look up. On a clear night, far from the city, the sky can be overwhelming. The Milky Way arches overhead in a pale river of light. Individual stars flicker and burn. If you look carefully, perhaps with a pair of binoculars, you might catch the faint smudge of the Andromeda Galaxy, our nearest large galactic neighbor. A soft oval of light that has been traveling toward your eyes for 2.5 million years. It looks small, unremarkable even, just a pale blur against the darkness. But Andromeda contains roughly 1 trillion stars. It spans 220,000 light years from edge to edge, and it is heading directly toward us at roughly 300 kilometers per second. In about 4.5 billion years, Andromeda and the Milky Way will collide, their spiraling arms reaching into each other like the fingers of two enormous hands, their stars rearranging into something entirely new. And yet, for all its size and drama, Andromeda is small. In the grand scheme of the universe, both it and our own Milky Way are specks. They belong to a modest gathering called the local group, a collection of more than 50 galaxies bound together by gravity, scattered across a region about 10 million light-years in diameter. The local group contains a few large spirals, a handful of irregulars, and dozens of tiny dwarf galaxies, many of them so faint and small that they were only discovered in the last few decades. But keep zooming out, pull the camera further and further back, and the local group itself shrinks into insignificance. It sits on the outer edge of a much larger assemblage, the Virgo supercluster, a vast cloud of galaxy groups and clusters centered on the massive Virgo cluster, which alone contains over 1,000 galaxies, all crammed into a region roughly 60 million light-years away. The Virgo cluster is enormous. It warps space-time. It bends the paths of galaxies around it, and it is just one knot in something incomprehensibly bigger. Because when you pull back far enough, when you map thousands, then millions, then billions of galaxies across the sky, you begin to see something emerge. Not randomness, not uniformity, but pattern. Galaxies are not scattered evenly across the cosmos like sugar sprinkled on a table. They are arranged, organized, strung out along thin, luminous threads that weave and twist through the darkness, connecting enormous clusters at their intersections, surrounding colossal empty regions where almost nothing exists at all. The whole thing looks organic, alive almost, like a network of neurons in a brain or the branching pattern of blood vessels in a lung. And this is the cosmic web. It is made of filaments, long, thin strands of galaxies, and dark matter and hot gas, stretching tens of millions, sometimes hundreds of millions of light years. Where filaments meet, they form nodes, dense clusters of galaxies bound together in seething gravitational knots. Between the filaments lie walls, flattened sheets of galaxies that form the membranes of enormous bubble-like structures. And inside those bubbles are the voids, barren, empty gulfs of space, hundreds of millions of light years across, containing almost nothing, not stars, not gas, not dark matter, just emptiness. Roughly 80% of the observable universe by volume is void. It is empty. Most of space is nothing, and the remaining 20%, where all the mass is concentrated, is organized into this intricate, web-like pattern that stretches across the entire cosmos. The question that haunted astronomers for decades and still haunts them today is, how did the universe go from the smooth, featureless fog that existed just after the Big Bang to this? How did nothing become everything? How did uniformity become structured? The answer involves invisible matter, frozen sound waves, the very first light that ever shone, a Swiss astronomer that nobody believed, and a supercomputer simulation so detailed that it can recreate the birth of galaxies from scratch. And it starts, as most great discoveries do, with someone paying very close attention to something that nobody else was looking at. For most of human history, the night sky appeared static, fixed. The stars held their positions like jewels mounted on a dark ceiling. and the planets wandered their predictable paths. The universe, as far as anyone knew, was small, orderly, and centered on Earth, even after Copernicus dislodged us from the center of the solar system, and Galileo turned his telescope skyward and saw mountains on the moon. The scale of the cosmos remained modest by modern standards. The stars were out there, yes, but how far out there, nobody really knew. It was not until the early 20th century that the universe revealed its true size, and it did so through a series of discoveries that shattered every assumption humanity had ever held about its place in the cosmos. In 1924, Edwin Hubble, working at the Mount Wilson Observatory in California, settled one of the great debates of astronomy. Using a powerful new 100-inch telescope, the largest in the world at the time, Hubble identified a type of pulsating star known as a Cepheid variable inside a fuzzy patch of light, then called the Andromeda Nebula. Cepheid variables are cosmic distance markers. The rate at which they brighten and fade is directly related to their intrinsic luminosity, which means that by measuring how bright they appear, you can calculate how far away they are. Hubble did the math, and the answer was staggering. The Andromeda Nebula was not a cloud of gas within our own galaxy, as many astronomers believed. It was an entirely separate galaxy, roughly 900,000 light-years away. The number was actually an underestimate. The true distance is about 2.5 million light-years, but the implication was earth-shattering regardless. The Milky Way was not the entire universe. It was one galaxy among how many? Thousands? Millions? The answer, as we now know, is hundreds of billions. At minimum, the observable universe contains somewhere around 2 trillion galaxies, stretching in every direction for 46 billion light-years. The scale is numbing. It defeats the human imagination so thoroughly that the numbers become almost meaningless. 2 trillion galaxies, 200 sextillion stars, a volume of space so large that light, the fastest thing in the universe, would need 93 billion years to cross it if the universe were not expanding, which of course it is. And that expansion was Hubble's next great discovery. In 1929, Hubble published evidence that distant galaxies are receding from us, and that the farther away a galaxy is, the faster it appears to be moving. This relationship, now known as Hubble's law, was the first observational evidence for the expansion of the universe. A prediction that had already been made on theoretical grounds by the Belgian priest and physicist Georges Lemaitre 2 years earlier. The universe was not static, it was growing. And if you ran the clock backward, the expansion implied that everything we see today was once compressed into an unimaginably hot, dense state. The Big Bang. But what mattered for our story is not just how many galaxies there are, or that the universe is expanding, but how those galaxies are distributed. Because for decades after Hubble's revelation, astronomers assumed the answer was, more or less evenly. The universe, they believed, was homogeneous, smooth. At large enough scales, one patch of sky should look pretty much like any other. This was not just an assumption, it was elevated to the status of a principle. The cosmological principle stated that, on sufficiently large scales, the universe is both homogeneous, the same everywhere, and isotropic, the same in every direction. It was a foundational assumption of modern cosmology. baked into Einstein's equations of general relativity and used to derive the expanding universe models that followed from Hubble's later discovery that galaxies are receding from one another. But assumptions, no matter how elegant, are not facts. And by the late 1970s, a small group of astronomers was about to prove that the universe's smoothness was an illusion. The story of how we first mapped the cosmic web begins in Cambridge, Massachusetts, at the Harvard-Smithsonian Center for Astrophysics. It was there, in 1977, that astronomers Mark Davis, John Huckra, Dave Latham, and John Tonry launched an audacious project, the CFA Redshift Survey. The idea was simple in concept, but grueling in practice. They would measure the redshifts of thousands of nearby galaxies. Redshift, in astronomical parlance, is the stretching of light toward redder wavelengths caused by the expansion of the universe. The farther away a galaxy is, the faster it is receding from us, and the more its light is shifted toward the red end of the spectrum. Measure the redshift, and you can calculate the distance. Do this for enough galaxies, and you can build a three-dimensional map of the universe. Before this survey, maps of the sky were essentially two-dimensional. Astronomers knew the positions of galaxies in the sky, their right ascension and declination, like longitude and latitude. But they had very limited information about depth. Without distances, you cannot distinguish between a galaxy that is bright and far away from one that is dim and nearby. You cannot tell if two galaxies that appear close together in the sky are actually neighbors in space or separated by hundreds of millions of light years along the line of sight. Redshift surveys changed all of this. By measuring the spectrum of each galaxy and extracting its redshift, astronomers could assign a distance and place each galaxy in three-dimensional space. The first phase of the survey was completed by 1982. It measured redshifts for over 2,400 galaxies, brighter than a certain magnitude limit. The results were interesting, but limited. Then, in 1985, John Huckra and Margaret Jeller began the second phase, CF ATWO. This was a far more ambitious undertaking. They aimed to measure redshifts for approximately 18,000 galaxies across the northern sky, probing deeper and wider than ever before. Margaret Jeller was a meticulous scientist with a gift for visualization. She understood that numbers on a page meant little unless you could see the patterns they contained. And so, as the data accumulated over months and years, she and Huckra plotted the galaxy positions in thin slices across the sky. Pie-shaped wedges that showed right ascension on the horizontal axis and distance, inferred from redshift, radiating outward from the center. When the first of these slices was completed, what they saw was not smooth. It was not random. It was not what the cosmological principle predicted at all. The galaxies were arranged on the surfaces of enormous bubble-like structures. Dense concentrations of galaxies formed thin walls and filaments, surrounding huge, empty regions where almost no galaxies existed. The overall impression was, as astronomer Valerie de Lapparent later described it, like looking at a cross-section through the suds in a kitchen sink. Galaxies sat on the surfaces of bubbles. The interiors of those bubbles were almost completely empty. One of the most striking images from the early survey was a famous pie-shaped, which that became known as the Stickman. because a prominent concentration of galaxies near the center of the slice resembled a stick figure with outstretched arms. It was an odd, whimsical nickname for what was actually a profoundly important piece of data. The first undeniable visual evidence that the universe had large-scale structure. The implications were immediate and far-reaching. If galaxies were arranged on the surfaces of bubbles, then the universe was not just clumpy. It was organized. There was a topology to the distribution of matter, a pattern that begged for explanation. What could create these bubble-like formations? What force could sweep galaxies onto thin surfaces and leave the interiors so barren? Margaret Geller was particularly struck by the clarity of the pattern. In interviews, she described the moment of seeing the first slice come together as one of genuine astonishment. She and Huckra had expected some degree of clustering, perhaps some hints of the superclusters that were already known, but the sharpness of the structures, the thinness of the walls, and the vastness of the voids were beyond anything they had anticipated. The universe was whispering a secret, and they were among the first to hear it. And then, in 1989, the full scope of the CF Atwos survey revealed something even more dramatic. A vast, thin, sheet-like structure of galaxies stretching across the entire width of the survey. It was roughly 500 million light-years long, 300 million light-years wide, and only about 15 million light-years thick. It was the single largest coherent structure that had ever been observed in the universe. They called it the Great Wall. The discovery of the Great Wall was a turning point. It proved beyond any doubt that the universe was not smooth. It was structured, and structured on scales far larger than anyone had imagined. The cosmological principle was not wrong exactly, but its domain of applicability was far narrower than people had assumed. At scales below a few hundred million light-years, the universe was wildly inhomogeneous, full of filaments, clusters, walls, and voids. Only at the very largest scales, above roughly 1 billion light-years, did the distribution of matter begin to even out. The Great Wall was a revelation, but it was also a challenge. What could possibly create a structure that big? What force could organize hundreds of thousands of galaxies into a thin sheet spanning 500 million light-years? The answer, it turned out, had been hiding in the oldest light in the universe. There is a wall of light surrounding us. It comes from every direction, at every moment, with perfect uniformity. It bathes the Earth in a faint glow of microwave radiation, invisible to human eyes, but detectable with the right equipment. It has been traveling toward us for over 13 billion years, and it carries within it a message from the very beginning of time. This is the cosmic microwave background, and it is the single most important observation in all of cosmology. The story of its discovery is one of science's great accidents. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were using a large horn-shaped antenna, originally built for satellite communications, to study radio signals from the Milky Way. But no matter where they pointed the antenna, no matter what time of day or what season of the year, they detected a persistent, low-level hiss of static. It came from every direction. It never went away. They checked the equipment. They cleaned pigeon droppings from the antenna horn. They cooled the receiver to eliminate thermal noise. Nothing worked. The hiss remained. What Penzias and Wilson had stumbled upon, almost entirely by accident, was the relic radiation from the Big Bang itself. In the first few 100,000 years after the birth of the universe, all of space was filled with a seething, opaque plasma, a screaming hot mixture of protons, electrons, and photons, all tangled together in a state of constant interaction. The photons could not travel freely. Every time one tried to move, it slammed into an electron and was deflected, then absorbed, then re-emitted in a random direction. The universe was foggy, opaque. Light could not escape, but the universe was expanding, and as it expanded, it cooled. And roughly 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees Kelvin, cool enough for the first time for electrons to combine with protons and form neutral hydrogen atoms. This event, called recombination, was a phase transition of cosmic proportions. Suddenly, the fog lifted. The photons were free, and they streamed outward in every direction, carrying with them a snapshot of the universe as it existed at that moment, 380,000 years after the beginning. Those photons have been traveling ever since. The expansion of the universe has stretched their wavelengths by a factor of roughly 1,100, cooling them from a blazing 3,000 degrees to a frigid 2.7 degrees above absolute zero. They now register as microwaves, and they fill every cubic centimeter of space, everywhere, at all times. There are roughly 411 of them in every cubic centimeter of the air around you right now. This is the cosmic microwave background. And for our story, what matters most about it is not its existence, but its imperfections. Because the CMB is not perfectly uniform, when you subtract the average temperature and look at the tiny deviations, the fluctuations, you find a pattern. Across the whole sky, the temperature varies by about 1 part in 100,000. Some spots are ever so slightly warmer. Others are ever so slightly cooler. The differences are minuscule, millionths of a degree, but they are there. And those tiny differences are the seeds of everything. The slightly warmer regions correspond to areas where the primordial plasma was ever so slightly less dense. The slightly cooler regions correspond to areas where it was ever so slightly denser. And those tiny variations in density, imprinted on the universe when it was less than 400,000 years old, are the blueprint from which the entire cosmic web would eventually be constructed. 3 separate space missions have mapped the CMB with increasing precision, each one sharpening the portrait. NASA's Cosmic Background Explorer, or COBE, launched in 1989, was the first to detect the tiny temperature fluctuations. COBE's instruments were revolutionary for their time, but their resolution was coarse. The satellite could see only the broadest features of the CMB's modeled pattern, like viewing a pointillist painting from across a football field. Even so, the detection was groundbreaking. When COBE project scientist John Mather and principal investigator George Smoot announced the results in 1992, Stephen Hawking reportedly called it the most important discovery of the century, if not of all time. The next step came with the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. WMAP mapped the CMB with 30 times better resolution and far greater sensitivity than COBE, revealing the fluctuations in exquisite detail. For the first time, cosmologists could measure the precise statistical properties of the pattern, how much power was concentrated at different angular scales, how the hot and cold spots were distributed, and what this told them about the geometry and composition of the universe. WMAPS data confirmed that the universe is geometrically flat, that it is about 13.7 billion years old, and that its contents are roughly 4.6% ordinary matter, 23% dark matter, and 72% dark energy. Then, in 2009, the European Space Agency launched the Planck satellite, the most sensitive CMB observatory ever built. Planck could detect temperature variations of just a few millionths of a degree. Its all-sky map, released in 2013, remains the definitive portrait of the infant universe. The picture it paints is both stunningly beautiful and almost impossibly informative. Every feature in that modeled pattern of blue and red and gold corresponds to a physical process occurring in the plasma of the early universe. The largest features were shaped by the initial conditions of inflation. The smaller features, the distinctive series of peaks and troughs visible in the angular power spectrum, are the frozen fingerprints of acoustic oscillations. Sound waves that rang through the primordial plasma for 380,000 years before the universe became transparent. And it is those sound waves, those frozen ripples, that connect the CMB to the cosmic web in a direct, physical, measurable way. Over the following billions of years, gravity would take those minute density fluctuations and amplify them. Regions that were slightly denser would gravitationally attract more matter, growing denser still. Regions that were slightly underdense would lose matter to their denser neighbors, growing emptier over time. It was a slow, relentless process, gravity carving structure from an almost perfectly smooth sheet of matter, pulling material into filaments and clusters and walls, leaving behind the vast, empty voids. But there was a problem. The fluctuations in the CMB were too small. The density differences were too tiny. If ordinary matter had been the only ingredient, gravity would not have had enough time in 13.8 billion years to build the structures we see today. The Great Wall, the galaxy clusters, the filaments, the voids. None of them should exist. The universe should still be nearly smooth. Something else was needed. Something that could start building structure earlier, before the fog cleared, before the CMB photons were released. Something that did not interact with light and therefore was not held back by the radiation pressure that prevented ordinary matter from clumping. Something invisible, something dark. In 1933, a Swiss astronomer named Fritz Zwicky was doing something that few of his colleagues considered worthwhile. He was studying a cluster of galaxies. Galaxy clusters were still a relatively new concept at the time. It had been less than a decade since Hubble had proven that galaxies existed beyond the Milky Way. And the idea that they might gather into enormous gravitationally bound groups was still being digested by the astronomical community. But Zwicky was not one to wait for consensus. He was brilliant, cantankerous, and famously difficult to work with. Born in Bulgaria in 1898 to a Swiss father and Czech mother, he spent most of his career at the California Institute of Technology in Pasadena, California, where his volcanic temperament and iconoclastic thinking made him both feared and underestimated. He called his colleagues at Caltech spherical bastards because, as he explained, they were bastards no matter which way you looked at them. He developed a systematic method of creative thinking he called morphological analysis, and he applied it with ruthless energy to every problem he encountered. He predicted the existence of neutron stars. He predicted gravitational lensing. He championed the use of wide-angle Schmidt telescopes for sky surveys. And on virtually every one of these ideas, he was right, and his colleagues were slow to acknowledge it. He was also, on this particular occasion, spectacularly right about dark matter. Zwicky was observing the Coma Cluster, a massive gathering of over 1,000 galaxies located roughly 320 million light-years away in the constellation Coma Berenices. He wanted to measure the mass of the cluster, and he chose to do so using a tool borrowed from thermodynamics, the virial theorem, which relates the average kinetic energy of a gravitationally bound system to its total gravitational potential energy. In plain language, if you measure how fast the galaxies in a cluster are moving, you can calculate how much gravity is needed to keep them from flying apart. And from that, you can estimate the total mass. Zwicky measured the velocities of the galaxies in the Coma Cluster by analyzing their redshifts. The galaxies were moving fast, very fast. Differences in velocity within the cluster exceeded 2,000 kilometers per second. When he applied the virial theorem, the mass he calculated was enormous, at least 400 times greater than the mass he could account for by adding up all the visible light from all the galaxies. Something was wrong. Either the cluster was flying apart, in which case it should not exist as a bound structure at all, or there was far more mass present than the stars could account for. Zwicky chose the latter interpretation. In his 1933 paper, written in German for the journal Helvetica Physica Acta, he described the discrepancy and introduced a term that would echo through the rest of the 20th century and beyond. He called it Dunkelmaterei, dark matter. The response from the scientific community was, for the most part, silence. Zwicky's personality did not help his cause. He was abrasive, confrontational, and prone to insulting anyone who disagreed with him. His ideas about dark matter, supernovae, neutron stars, and gravitational lensing were either ignored or actively dismissed by his peers during his lifetime. It would take 40 years and the work of another stubborn, underestimated astronomer to bring the dark matter problem back to the forefront. Her name was Vera Rubin. Working at the Carnegie Institution of Washington in the 1970s, Rubin was studying something more accessible than galaxy clusters: the rotation curves of individual spiral galaxies. A rotation curve is a plot of orbital velocity versus distance from the center of a galaxy. According to Newton's laws, stars orbiting far from the bright central bulge of a galaxy should be moving more slowly than stars close in, just as Neptune orbits the Sun more slowly than Mercury. The mass is concentrated in the center, so gravity weakens with distance, and orbital speeds should decline. But that is not what Rubin found. Working with instrument maker Kent Ford, who had developed an exceptionally sensitive spectrograph capable of measuring faint spectral lines from the outer edges of spiral galaxies. She measured the rotation curves of dozens of galaxies, and in every single one, the pattern was the same. Stars near the edges of the galaxy were orbiting just as fast as stars near the center. The rotation curves were flat. They did not decline. This was deeply unsettling. It violated the most basic expectations of Newtonian gravity applied to the visible mass distribution of galaxies. And it was not a subtle effect. The discrepancy was enormous. In some galaxies, the outermost stars were orbiting so fast that they should have been flung out into intergalactic space long ago. Unless there was far more gravitational pull holding them in place than the visible stars could account for. Rubin published her results methodically, galaxy after galaxy, building an overwhelming case. By 1980, she and Ford had measured the rotation curves of more than 60 spiral galaxies, and the conclusion was inescapable. The visible matter in galaxies, the stars and gas and dust that emit light and can be seen with telescopes, accounts for only a fraction of the total mass. The rest is invisible, distributed in a vast, extended halo that surrounds each galaxy, reaching far beyond the visible disk. This meant one of two things. Either Newton's law of gravity was wrong at galactic scales, or there was far more mass in these galaxies than the visible stars could account for, and that mass had to be distributed in a vast, extended halo surrounding each galaxy, far beyond the visible disk of stars. Rubin had confirmed Zwicky's suspicion on an entirely different scale. Using an entirely different method, galaxies were embedded in enormous cocoons of invisible matter. The stuff we could see, the stars and gas and dust, was just the froth on top. The real substance of the universe was hidden. Rubin herself put it simply and memorably. In a spiral galaxy, the weights of light and darkness are reversed. 90% or more of the matter in the universe is dark. Despite the strength of her evidence, Rubin faced skepticism and resistance. She was working in a field dominated by men, in an era when women in astronomy faced significant barriers. She had been denied admission to Princeton's astronomy graduate program because the university did not accept women at the time. She persevered nonetheless, and her work, along with Zwicky's earlier insights, ultimately reshaped our understanding of the universe. Though she was widely considered deserving of a Nobel Prize, she never received one before her death in 2016. And here is where this connects to the cosmic web, because dark matter is not just a curiosity or an accounting error. He is the architect of cosmic structure. Remember the problem with the CMB fluctuations. The density variations in ordinary matter were too small, and gravity had not had enough time to build the structures we see today. Dark matter solves this problem, and it does so because of a critical difference in its behavior. Ordinary matter in the early universe was coupled to radiation. The photons and the protons and the electrons were all tangled together in the hot plasma before recombination, and radiation pressure fought against gravitational collapse. Every time gravity tried to pull ordinary matter into a denser clump, the pressure of the photons pushed it back out. Ordinary matter could not begin to collapse into structures until after recombination, when the photons decoupled and the pressure vanished. That was 380,000 years after the Big Bang. But dark matter does not interact with light. It does not feel radiation pressure. It is invisible. It passes through photons like a ghost passes through a wall. And because of this, dark matter could begin collapsing under its own gravity immediately, long before recombination, long before the CMB was released. Dark matter was already pulling itself into denser and denser concentrations. The first skeletal outlines of the cosmic web by the time the universe became transparent and ordinary matter was finally free to move. The dark matter scaffolding was already in place. Ordinary matter simply fell into the gravitational wells that dark matter had prepared for it, like water flowing into valleys that had already been carved. The galaxies that formed, the clusters that assembled, the filaments that stretched across space. All of them followed the invisible blueprint laid down by dark matter in the first moments of cosmic history. This is not speculation. It is one of the most well-tested predictions in cosmology. Computer simulations that start with the observed properties of the CMB and include dark matter as the dominant gravitational component produce cosmic webs that match observations with extraordinary precision. The number of galaxy clusters, the lengths of filaments, the sizes of voids, the statistical clustering of galaxies at different scales, all of these match. Remove dark matter from the simulation and the match vanishes. The structures are too small, too sparse, and too weakly developed. Dark matter is not optional. It is the essential ingredient. We still do not know what dark matter is made of. Despite decades of experimental searches, no dark matter particle has been detected in a laboratory. The leading candidates include weakly interacting massive particles, hypothetical particles left over from the Big Bang that interact with ordinary matter only through gravity, and the weak nuclear force, and axions. Extremely light, hypothetical particles originally proposed to solve a different problem in particle physics. Numerous experiments around the world are searching for both, buried deep underground to shield them from cosmic rays, cooled to near absolute zero to minimize thermal noise, and instrumented with the most sensitive detectors ever built. So far, the universe has kept its secret. But whatever dark matter is made of, its gravitational effects are unmistakable. It built the cosmic web. It holds galaxies together. It bends the paths of light through gravitational lensing, and it outweighs ordinary matter by a factor of roughly 5-1. Dark matter makes up roughly 85% of all the matter in the universe. Only about 15% is ordinary baryonic matter, the stuff that makes up stars and planets and people. And it is this invisible majority that determined the shape of the cosmic web. The galaxies we see are the luminous tips of a vast iceberg. They trace the dark matter distribution, like Christmas lights draped over a frame that you cannot see. Without dark matter, there would be no cosmic web. There would be no galaxies. There would be no stars, no planets, no chemistry, no life. The invisible has given rise to everything visible, and the invisible followed a very specific set of rules. The universe did not build the cosmic web all at once. It was a gradual process, unfolding over billions of years, driven by the relentless, patient tug of gravity, acting on the density fluctuations left over from the very earliest moments of cosmic history. To understand how it happened, we need to travel back to the first fraction of a second after the Big Bang, to a period called inflation. Inflation is one of the most remarkable ideas in all of physics, and its story is almost as dramatic as the phenomenon it describes. It was proposed independently by several physicists in the late 1970s and early 1980s, most notably by Alan Guth at MIT, Andrei Linde in the Soviet Union, and Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania. Each was trying to solve a different puzzle about the early universe, but all arrived at a similar conclusion. The universe must have undergone a brief, explosive period of exponential expansion in its very first moments. The problems that inflation was designed to solve were real and pressing. First, there was the horizon problem. The cosmic microwave background is almost perfectly uniform in temperature across the entire sky, even in regions that are so far apart that they could never have been in causal contact with each other. How could regions of the universe that had never exchanged information arrive at the same temperature? Second, there was the flatness problem. The geometry of the universe appears to be almost perfectly flat, which requires an extraordinarily precise balance between the energy of expansion and the pull of gravity. Even a tiny deviation in the first moments would have led to a universe that was either hopelessly curved or rapidly collapsing. How could this fine-tuning have arisen? Inflation solved both problems in one elegant stroke. It proposes that the universe, in the first unimaginably tiny sliver of time after its birth, we are talking about the first 10 to the negative 36th seconds or so, underwent a brief but violent period of exponential expansion. In that instant, the observable universe ballooned from something far smaller than a proton to something roughly the size of a grapefruit. Then inflation ended, and the universe settled into the more leisurely expansion we observe today. Inflation smoothed out the universe almost perfectly. It stretched space until it was flat, uniform, and featureless. But crucially, it did not smooth it out completely. Quantum mechanics, the physics of the very small, ensured that there were tiny random fluctuations in the energy density of the inflating field. These quantum fluctuations were unimaginably small, but inflation stretched them to macroscopic scales, imprinting them across the entire cosmos. When inflation ended, these fluctuations became the seed density perturbations in the matter and energy that filled the newborn universe. Some regions were ever so slightly denser than average. Others were ever so slightly less dense. The differences were minuscule, about 1 part in 100,000. But that was enough, because gravity is patient. In the regions that were slightly overdense, the extra matter exerted a slightly stronger gravitational pull on its surroundings, drawing in more material. This made those regions even denser, which increased their gravitational pull further, which drew in still more material. It was a feedback loop, slow at first, but inexorable. Over hundreds of millions of years, the denser regions grew denser, and the underdense regions grew emptier. But the collapse did not happen uniformly in all directions. This is a critical point, and one that was first understood by the Soviet physicist Yakov Zeldovich in the 1970s. Zeldovich was one of the giants of 20th century physics, a man who contributed to the Soviet nuclear weapons program before turning his formidable intellect to cosmology. He realized that because the initial density fluctuations were not perfectly spherical, but instead slightly elongated or flattened in various directions, gravitational collapse would not produce spheres. Instead, matter would first collapse along one axis, forming flat, sheet-like structures that Zeldovich called pancakes. These sheets would then compress further along a second axis, forming elongated filaments, and finally, the filaments would contract along their remaining axis, forming dense, compact nodes. The sequence is elegant in its simplicity. Gravity attacks the path of least resistance first. It collapses matter along the shortest dimension, because that is where the material has the least distance to travel. Think of a slightly oblong cloud of gas. Gravity first flattens it into a sheet because the shortest axis collapses first. Then it squeezes the sheet into a filament. Then it compresses the filament into a knot. Sheet, filament, node, wall, thread, cluster. The cosmic web writes itself, step by step, out of the physics of gravitational collapse. Later work by cosmologist Richard Bond and his collaborators in the 1990s refined Zeldovich's picture. They showed that the dominant features of the cosmic web are filaments, not sheets, because the gravitational influence of nearby density peaks creates a network of ridgelines connecting one peak to the next. Imagine a mountain landscape where every mountain peak is connected to its neighbors by saddle ridges. The ridges are the filaments, the peaks are the clusters, and the valleys between them are the voids. This insight, which Bond and his colleagues called the cosmic web, they are credited with popularizing the term, provided a powerful framework for understanding how large-scale structure arises from the initial conditions measured in the CMB. This is precisely what we observe in the cosmic web. The sheets, or walls, are the broadest and thinnest features. The filaments are denser and more elongated. The nodes, where filaments intersect, are the densest regions of all, and they are where the largest galaxy clusters reside. The voids are the regions that lost their matter to the surrounding structures, the spaces between the sheets and filaments that grew ever emptier over cosmic time. The process is known as hierarchical structure formation, and it is one of the defining features of the cold dark matter model that is the current standard in cosmology. In this model, small structures form first. Tiny clumps of dark matter collapse early, creating miniature gravitational wells called dark matter halos. These halos then merge with one another over time, building progressively larger structures. Small halos merge to form larger halos. Galaxies form within halos. Galaxy groups form as halos cluster together. Galaxy clusters assemble at the densest intersections of the cosmic web, growing through the steady accretion of smaller structures over billions of years. The term cold in cold dark matter refers to the speed of the dark matter particles in the early universe. Cold dark matter particles move slowly compared to the speed of light. This is important because it determines the minimum size of the structures that can form. If the dark matter were hot, meaning its particles moved at high speeds, as neutrinos do, the particles would have streamed freely through space in the early universe, erasing density fluctuations below a very large scale. In a hot, dark matter universe, the first structures to form would be enormous, and smaller structures like galaxies would have to form later by fragmentation. This is called the top-down scenario, and it was the leading model in the early 1980s, but observations killed the hot, dark matter model. The cosmic web we observe has too much small-scale structure, too many individual galaxies and galaxy groups for the top-down scenario to work. Instead, the bottom-up scenario of cold, dark matter fits the data far better. The smallest structures form first. They merge into larger ones. The universe builds itself from the ground up, like a city assembled brick by brick. Rather than carved from a single monolithic block, the universe builds itself from the bottom up. Atoms become stars. Stars become galaxies. Galaxies become groups and clusters. And clusters connect along filaments to form the vast, interconnected web that spans the cosmos. But there is another piece of the puzzle embedded in the cosmic web, a relic of the sound waves that once rang through the entire universe. In the first 380,000 years after the Big Bang, before recombination, the universe was a hot, dense plasma, and in that plasma, the competition between gravity and radiation pressure created something extraordinary: sound waves. The slightly overdense regions of the plasma tried to collapse under gravity, but the intense radiation pressure of the photons resisted this collapse and pushed the matter back outward. The result was an oscillation. Matter compressed, rebounded, compressed again, rebounded again. Over and over, these were actual acoustic waves. Sound waves propagating through the plasma at roughly half the speed of light. When recombination occurred and the photons were released, these sound waves froze in place. They stopped propagating and left their imprint on both the distribution of matter and the cosmic microwave background. The distance that the sound waves had traveled from the Big Bang to recombination defined a characteristic scale, roughly 490 million light-years in today's expanded universe. This means that there is a slight statistical preference for galaxies to be separated by that particular distance. Not every pair of galaxies, of course, but on average, across the whole sky, there are slightly more galaxy pairs separated by about 490 million light-years than by other distances. These frozen sound waves are called baryon acoustic oscillations, and they serve as a cosmic ruler. Because we know the physical size of this imprint, it is set by well-understood physics in the early universe. We can use it to measure distances across the cosmos with remarkable precision. As the universe expands, the baryon acoustic oscillation scale stretches along with it. And by measuring how that scale appears at different epochs of cosmic history, astronomers can trace the expansion rate of the universe over time. Think of it this way. Imagine dropping a pebble into a perfectly still pond. A ring of ripples expands outward from the point of impact. Now, imagine freezing the pond at the instant the ripple reaches a specific diameter. That frozen ring is analogous to the baryon acoustic oscillation signal. Now imagine that the frozen pond slowly stretches over time. If you know the original diameter of the ring, you can measure how much the pond has stretched by comparing the original diameter to its current apparent size. The baryon acoustic oscillation signal works the same way. Astronomers know the original size of the sound horizon, roughly 490 million light-years in today's expanded universe. By measuring how that preferred galaxy separation appears at different redshifts, they can determine how much the universe has expanded between then and now. The first detection of the baryon acoustic oscillation signal in the distribution of galaxies came in 2005, when Daniel Eisenstein and his colleagues at the Sloan Digital Sky Survey identified a subtle peak in the correlation function of luminous red galaxies. This peak, appearing at a separation of roughly 500 million light-years, was precisely where theory predicted it should be. It was a stunning confirmation that the same sound waves imprinted on the cosmic microwave background 380,000 years after the Big Bang were still visible in the distribution of galaxies. 13 billion years later, the universe carries its childhood with it. The echoes of its earliest moments are embedded in its current structure, waiting to be read by anyone with the right instruments and the patience to look. This cosmic ruler is woven into the fabric of the cosmic web itself. It is one of the key tools that modern surveys use to map the large-scale structure of the universe and to investigate the nature of dark energy, the mysterious force driving the accelerating expansion of the cosmos. We will return to dark energy later. But first, let us examine the architecture of the web itself more closely. The cosmic web is not a metaphor. It is not a poetic flourish. It is a physical structure, as real as a mountain range or an ocean basin, although incomparably larger. And like any structure, it has anatomy, distinct components that serve different roles and exist at different scales. The most prominent features of the cosmic web are the filaments. These are the threads, the strands, the long luminous highways of matter that connect the densest regions of the universe. A typical filament is a few million light-years wide, but can stretch for tens or even hundreds of millions of light-years. The largest filament measured to date, known as Kipu, extends for roughly 1.3 billion light-years. Filaments are not solid ropes of galaxies. Instead, they are elongated regions of higher than average density, containing galaxies, dark matter, and vast quantities of hot, diffuse gas known as the warm-hot intergalactic medium. Galaxies within filaments are not stationary. They move along the filaments, drawn by gravity toward the massive clusters at the nodes. Computer simulations show this beautifully. Streams of galaxies flowing along filaments like traffic on a highway, converging at the intersections where clusters of galaxies sit. The process is continuous and ongoing. New gas flows into the filaments from the surrounding voids, feeding the galaxies within them. Galaxies grow, merge, and evolve as they slide along the filaments toward their ultimate destination, the dense, violent environments of galaxy clusters. This gas is one of the most elusive components of the cosmic web. It exists at temperatures ranging from 100,000 to tens of millions of degrees Kelvin, too hot to be detected in visible light, too cool and diffuse to shine brightly in X-rays. For decades, astronomers suspected that the warm-hot intergalactic medium contained a large fraction of the ordinary matter in the universe, the so-called missing baryons, which were expected to exist based on Big Bang nucleosynthesis calculations, but had never been directly observed. The missing baryon problem was a genuine puzzle. The amount of ordinary matter produced in the first few minutes after the Big Bang can be calculated with great precision from the observed abundances of hydrogen, helium, and lithium. But when astronomers added up all the ordinary matter they could actually detect in stars, in cold gas, in hot galaxy cluster gas, the total fell short by roughly half. Where was the rest? The answer, predicted by simulations and gradually confirmed by observations, was in the filaments of the cosmic web. The warm-hot intergalactic medium is a vast reservoir of heated gas, shock-heated as it falls into the gravitational potential wells of the filaments, too tenuous to form stars, but containing an enormous total mass. Only in recent years have sensitive ultraviolet observations, advanced X-ray spectroscopy, and new techniques like fast radio burst dispersion measurements begun to confirm that this gas really does pervade the filaments, accounting for much of the matter budget that had been unaccounted for. In 2020, a team of astronomers used fast radio bursts, brief but powerful flashes of radio energy from distant galaxies, to measure the total amount of ionized gas along different lines of sight through the cosmic web. Their results matched the predictions of simulations. The missing baryons were hiding in plain sight, woven into the filaments that connect galaxies across the cosmos. Where filaments intersect, they form nodes. These are the densest, most massive structures in the cosmic web, and they correspond to galaxy clusters, titanic congregations of hundreds or thousands of galaxies, bound together by gravity, immersed in vast clouds of superheated gas, and saturated with dark matter. The most massive galaxy clusters contain trillions of solar masses of material. They are the largest gravitationally bound objects in the universe, and their growth is directly tied to their position at the crossroads of the cosmic web's filamentary highways. Consider the Coma Cluster, the same collection of galaxies that Fritz Zwicky studied in 1933. It contains over 1,000 galaxies, sits at the intersection of multiple filaments, and is embedded in a cloud of gas so hot, over 100 million degrees Kelvin, that it glows brightly in X-rays. The Coma Cluster is roughly 320 million light-years from Earth, and it anchors one end of the Great Wall that Geller and Huckra discovered. Closer to home, the Virgo Cluster, which dominates the gravitational landscape of the local universe, contains over 2,000 galaxies and spans roughly 15 million light-years. At the center of the Virgo Cluster sits the giant elliptical galaxy MADI 7, famous as the host of the first black hole ever directly imaged by the Event Horizon Telescope in 2019. That supermassive black hole, with a mass of 6.5 billion suns, launches a relativistic jet of plasma that stretches 5,000 light-years into intergalactic space. It is a reminder that the densest nodes of the cosmic web are not peaceful places. They are sites of extraordinary violence and energy, where supermassive black holes gorge on infalling gas and blast their surroundings with jets powerful enough to heat the intergalactic medium for millions of light-years in every direction. Then there are the walls, or sheets. These are flattened, membrane-like structures of galaxies and dark matter that form the boundaries between voids. They are thinner and less dense than filaments, but far more extended, stretching across hundreds of millions of light years. The Great Wall, discovered in 1989, is one example. Another is the Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey. The Sloan Great Wall is even larger, roughly 1.37 billion light-years in length, making it one of the most immense coherent structures ever mapped. And then there are the voids. If the filaments and clusters and walls are the bones and sinews of the cosmic web, the voids are the empty spaces within it, the bubbles inside the foam, and they are enormous. The most famous void is the Boots Void, discovered in 1981 by astronomer Robert Kirshner and his colleagues during a redshift survey. It sits in the direction of the constellation Boots, roughly 700 million light-years from Earth, and it spans approximately 330 million light-years in diameter. To date, only about 60 galaxies have been found inside it. To put that in perspective, if you were to calculate how many galaxies you would expect in a volume of space that size, based on the average density of the universe, the answer would be roughly 2,000. The Boots Void contains about 3% of what it should. Astronomer Greg Aldering once offered a vivid illustration of what the Boots Void means in human terms. If the Milky Way had been located at the center of the Boots Void, he said, we would not have known that other galaxies existed until the 1960s. Until then, our telescopes would not have been powerful enough to detect galaxies across such vast distances of empty space. We would have looked out and seen nothing but darkness, convinced that we were alone. Imagine that for a moment. Picture growing up on a planet where every astronomer, every philosopher, every curious child who ever looked up at the sky saw only the stars of their own galaxy, surrounded on all sides by an abyss of absolute nothingness. No Andromeda smudge on the horizon, no Virgo cluster glowing in X-rays, no distant quasars blazing from the depths, just darkness. We would have believed, with total sincerity, that the Milky Way was the entire universe, that there was nothing else. And we would have been wrong, of course, but we would have had no way of knowing it. That is what a void can do. It can hide the universe from itself. The Boots Void is not unique, merely extreme. Closer to home, there is the local void, a barren region roughly 150 million light-years across that sits right on the edge of our own local group of galaxies. The center of the local void is estimated to be at least 75 million light-years from Earth. So far, only a single lonely dwarf galaxy has been found traveling through its interior, racing toward the boundary at over 200 kilometers per second, as if desperate to escape. Meanwhile, our own Milky Way and its neighbors are being pushed away from the local void at roughly 260 kilometers per second. One of three distinct components of our galaxy's complex motion through space. Further out, there are hints of even larger voids. The Eridanus supervoid, if it exists, could span 500 million light-years or more, and it has been tentatively linked to a puzzling cold spot in the cosmic microwave background, a region where the CMB temperature is slightly lower than expected. The cold spot could be caused by the integrated Sachs-Wolf effect, in which CMB photons lose a tiny amount of energy as they pass through a vast, low-density region of space. The connection is debated, but it illustrates how the cosmic web's voids can leave their fingerprints even on the oldest light in the universe. The voids are not truly empty, of course. They contain trace amounts of dark matter and gas, and a smattering of lonely galaxies that wander through their interiors like hermits in a desert. But compared to the rest of the cosmic web, they are desolate. They are the places the universe has abandoned, and they are growing. As the cosmic web evolves and gravity continues to pull matter into denser structures, the voids expand, growing emptier and emptier over time. In a sense, the history of the cosmic web is a story of contrast. The rich getting richer and the poor getting poorer, played out across billions of light years and billions of years. Together, the filaments, nodes, walls, and voids create a pattern that permeates the entire observable universe. It is a pattern that looks the same from every direction and at every scale up to a point, a foam-like network of matter surrounding vast empty regions, stretching as far as the most powerful telescopes can see. And at the center of one small, unremarkable region of that web sits our home. For most of the history of astronomy, we knew our cosmic address only in the most general terms. Earth orbits the sun. The sun orbits the center of the Milky Way, a spiral galaxy of perhaps 200 to 400 billion stars. The Milky Way belongs to the local group. The local group sits on the outskirts of the Virgo supercluster. Beyond that, things got vague. The concept of a supercluster was introduced in the 1950s by the French-American astronomer Gerard de Vaucouleurs, who noticed that the galaxies near the Milky Way were not uniformly distributed, but instead seemed to be concentrated in a flattened structure centered on the Virgo cluster. He called this the local supercluster. But the boundaries of superclusters were fuzzy and ill-defined. Where did one supercluster end and another begin? Without a clear definition, the question seemed almost unanswerable. Then, in 2014, a team of astronomers led by Brent Tully at the University of Hawaii changed everything. Tully and his colleagues took a fundamentally different approach. Instead of defining superclusters based on the density of galaxies, they defined them based on the flow of galaxies. Using a catalog of peculiar velocities, the motions of galaxies, after subtracting the general expansion of the universe, they mapped the gravitational landscape of the local cosmos. They were looking for watersheds, boundaries where the flow of galaxies diverged, just as water on a continental divide flows in different directions, depending on which side of the ridge it falls on. What they found was stunning. The Milky Way, the local group, the Virgo cluster, and a vast number of other structures were all flowing toward a common gravitational center, pulled by an enormous concentration of mass located in the direction of the constellations Centaurus and Norma. This concentration, long known to astronomers as the Great Attractor, turned out to be the gravitational heart of a supercluster far larger than the traditional Virgo supercluster. Tully's team defined this supercluster as the entire volume within which galaxy motions are directed inward toward the Great Attractor. It encompassed roughly 100,000 galaxies, spanned about 500 million light-years in diameter, and contained a total mass equivalent to 100 quadrillion suns. They named it Laniakea, a Hawaiian word meaning immense heaven. The name was suggested by Naua Napoleon, an associate professor of Hawaiian language at Kapiolani Community College, in a beautiful nod to the Polynesian navigators who once read the stars to cross the Pacific Ocean, just as those ancient voyagers used their knowledge of the heavens to navigate vast stretches of open water. Modern astronomers were using the motions of galaxies to navigate the gravitational currents of the cosmic ocean. Tully described his work using an analogy drawn from physical geography. Imagine the surface of the Earth, with its mountain ranges and river valleys and continental divides. Raindrops that fall on one side of a watershed flow toward one ocean. Raindrops that fall on the other side flow toward a different ocean. The divide itself is the boundary between two drainage basins. Tully was doing the same thing with galaxies. He was tracing the gravitational drainage basins of the cosmos, identifying where the flow of galaxies diverged, and using those boundaries to define the edges of superclusters. It was a fundamentally new way of thinking about cosmic structure, one based not on where galaxies are, but on where they are going. The discovery was published as the cover story of the journal Nature in September of 2014, and it generated worldwide attention. For the first time, humanity had a map of its cosmic neighborhood that showed not just the positions of galaxies, but the gravitational currents that bind them together. The visualization that accompanied the paper, created by Daniel Pommard, showed rivers of galaxies flowing inward toward the Great Attractor, converging from hundreds of millions of light years away. All of them swept along by the curvature of space-time that the cluster's immense mass creates. Laniakea redefined our cosmic address. The Milky Way sits near the edge of this supercluster, close to the boundary between Laniakea and the neighboring Perseus-Pisces supercluster. We are not at the center of anything. We are on the outskirts, perched on the ridgeline of a cosmic continental divide. And Laniakea itself is just one part of a larger structure. In 2020, a team led by Daniel Pommard, Tully, and their collaborators discovered the South Pole Wall, an enormous arc of galaxies that wraps around Laniakea from behind, stretching in a great curve across more than 200 degrees of the sky. The South Pole Wall is roughly 1.4 billion light-years long, making it one of the largest coherent structures in the nearby universe. Portions of this wall lie just 300 million light-years from the Milky Way, making it one of the nearest large-scale features of the cosmic web. And yet, despite its proximity, the South Pole Wall had gone undetected for decades, because much of it lies behind the zone of avoidance, hidden by the dust and gas in the plane of our own galaxy. Its discovery was a vivid reminder that even in the age of space telescopes and billion-dollar surveys, the cosmic web still has secrets to reveal in our own cosmic backyard. The gravitational pull of the Great Attractor, meanwhile, is not the end of the story. Laniakea, along with several neighboring superclusters, appears to be moving toward an even larger concentration of mass, the Shapley concentration, a colossal assembly of galaxy clusters located roughly 650 million light-years away. Whether Laniakea and the Shapley concentration are part of some even grander structure remains an open question. But recent observations using the Cosmic Flossminus 4 catalog of galaxy distances have suggested that the boundaries of our cosmic neighborhood may extend even further than Tully's original mapping revealed. the Great Attractor itself is somewhat misleadingly named. It is not a single object, not a supermassive black hole or an enormous galaxy sitting at the center of everything. It is a broad, gravitationally influential region anchored by the Norma cluster and surrounding concentrations of galaxies and dark matter. The mass concentrated in this region is staggering. Estimates suggest something on the order of 100 quadrillion solar masses, spread across a volume hundreds of millions of light years wide. For decades, its nature was obscured by the zone of avoidance, the band of dust and gas in the plane of the Milky Way that blocks our view of roughly 20% of the sky. This is one of the great frustrations of extragalactic astronomy. Our own galaxy's disk, which is so beautiful when viewed from a dark hilltop, is also a veil that hides a significant fraction of the universe from our instruments. But infrared and X-ray observations have gradually peeled back the veil, revealing the rich structure that lies hidden behind our own galaxy's disk. Infrared light can penetrate the dust that blocks visible light, and X-ray emissions from hot intracluster gas can be detected regardless of foreground obscuration. Surveys using these wavelengths have revealed the Norma cluster and its surroundings in increasing detail, confirming that the Great Attractor region is a genuine, massive concentration of matter, not a mirage or an artifact of incomplete surveys. Follow-up studies by Tully's group have continued to expand our understanding of the gravitational landscape. In recent years, observations using the Cosmic Flow-Minus 4 catalog of galaxy distances have identified another potentially significant basin of attraction centered on the Ophiuchus cluster, which may be associated with Laniakea, and both Laniakea and this Ophiuchus region appear to be moving toward the even more massive Shapley concentration, a colossal assembly of galaxy clusters located roughly 650 million light-years away, suggesting that the gravitational hierarchy may extend to even larger scales than Tully's original mapping revealed. The cosmic web is fractal in a loose sense. At every scale you examine, there is more structure, more organization, more evidence that gravity has been at work. What Laniakea tells us is profound. It tells us that even at scales of hundreds of millions of light years, the universe is organized. There are attractors, basins of flow, watersheds, and boundaries. Galaxies are not wandering aimlessly. They are following the contours of a gravitational landscape sculpted by dark matter. And that landscape has structure at every scale we have been able to probe. Our place in the cosmos is not random. It is a specific address within a specific structure, within a specific web. And that web has features that push the limits of what physics can explain. The discovery of the Great Wall in 1989 was just the beginning, as surveys grew larger and more sensitive over the following decades. Astronomers kept finding bigger and bigger structures, each one pushing against the boundaries of what the standard cosmological model predicted should be possible. In 2003, analysis of data from the Sloan Digital Sky Survey revealed the Sloan Great Wall, a filament of galaxies roughly 1.37 billion light-years in length. It dwarfed the original Great Wall by a factor of nearly 3. It was, at the time, the largest known structure in the observable universe. But its reign did not last. In 2012, a team of astronomers announced the discovery of the huge, large quasar group, a collection of 73 quasars spanning roughly 4 billion light years. Quasars are the intensely bright cores of distant galaxies, powered by supermassive black holes devouring enormous quantities of gas. Because they are so luminous, they can be observed at enormous distances, serving as beacons that illuminate the large-scale structure of the early universe. The huge, large quasar group suggested the presence of an enormous overdensity of matter in a region far larger than the standard model comfortably predicted. And then, in 2013, things got truly extreme. A team of American and Hungarian astronomers led by Istvan Horváth, John Hakila, and Zsolt Baguli was analyzing data from the Swift gamma-ray burst mission. Gamma-ray bursts are the most powerful explosions in the universe, produced during events like the core collapse supernovae that birth black holes and the mergers of neutron stars. Because these explosions are so energetic, they can be detected across enormous distances. And because they are associated with regions of high star formation, and therefore high concentrations of matter, their distribution across the sky can be used as a tracer of large-scale structure. What the team found was a concentration of gamma-ray bursts at a distance of roughly 10 billion light years, clustered in a region of the sky centered on the constellations Hercules and Corona Borealis. The clustering was statistically significant, and it suggested the presence of a vast structure that the team estimated to be approximately 10 billion light years across. They called it the Hercules Corona Borealis Great Wall, and if it is real, it is the largest known structure in the observable universe, spanning roughly a tenth of the diameter of the entire observable cosmos. The name itself has an unusual origin. It was coined not by the discoverers, but by a Filipino teenager named Jondrick Valdez, who read a news report about the discovery and added an article about it to Wikipedia, giving the structure its now familiar name. The astronomers themselves subsequently adopted it, a charming reminder that in the age of the internet, the naming of cosmic structures is no longer the exclusive province of professional scientists. The Hercules Corona Borealis Great Wall is controversial. Some studies have questioned whether the observed clustering of gamma-ray bursts might be a statistical artifact, a fluke produced by the relatively small sample size and potential biases in the data. A 2016 study found that the distribution was consistent with what could be produced by random chance, though the result fell just below the 95% significance threshold. But a 2020 paper by the original discoverers, using a larger and more reliable dataset, found that the structure remained statistically significant. In 2025, a reanalysis of 542 gamma-ray bursts with known redshifts suggested that the structure might actually be even larger than originally estimated, possibly extending up to 15 billion light years, making it, if confirmed, even more troublesome for standard cosmology. A proposed European Space Agency mission called Theseus could eventually provide the definitive answer, with its ability to detect thousands of new gamma-ray bursts from very distant and faint sources. The problem is this: the cosmological principle predicts that, at large enough scales, The universe should appear smooth and uniform. There should be a maximum scale for structures, a threshold beyond which the distribution of matter becomes homogeneous. This threshold, sometimes poetically called the end of greatness, is estimated to lie somewhere around 700 to 1,200 million light years. Beyond that scale, structures should not exist. If you take a cube of the universe larger than this threshold and compare it to another cube of equal size from a different region, they should contain roughly the same amount of matter, the same number of galaxies, and the same statistical properties. The universe at sufficiently large scales should be boring, uniform, featureless, and to a large degree, this prediction holds. The cosmic microwave background, which probes the universe at a time before structures had formed, is uniform to 1 part in 100,000. Galaxy surveys, when averaged over sufficiently large volumes, do converge toward uniformity. The cosmological principle is not wrong, but the Hercules Corona Borealis Great Wall, if real, raises uncomfortable questions about where exactly the transition to homogeneity occurs, and whether our current statistical methods are adequate to identify it. The Hercules Corona Borealis Great Wall, if real, blows past this limit by a factor of 10. So does the huge, large quasar group to a lesser degree. These structures suggest that the universe might have more large-scale organization than the standard model predicts, which either means our statistical methods are flawed, our surveys are biased, or there is something fundamental about the cosmos that we do not yet understand. This is one of the great open questions in cosmology. The cosmic web, at scales of tens to hundreds of millions of light years, is well understood and well matched by our theoretical models. But at the very largest scales, the universe may be hiding surprises that our current theories cannot account for. And to investigate those surprises, astronomers have turned to a remarkable tool, the digital universe. But before we enter the world of supercomputer simulations, there is one more astonishing connection worth mentioning. In 2020, a team of researchers at the University of California, Santa Cruz, published a study that drew an unexpected bridge between biology and cosmology. They fed a slime mold, a simple single-celled organism called Physarum polycephalum, a pattern of food sources arranged to match the positions of galaxies in the local universe. Slime molds are remarkable organisms when they forage for food. They grow networks of thin filaments that connect food sources with extraordinary efficiency, minimizing the total length of the network while ensuring connectivity. Essentially, slime molds solve optimization problems that even sophisticated computer algorithms struggle with. The researchers found that the slime mold's network of filaments bore a striking resemblance to the cosmic web. The organism, guided by nothing more than chemical gradients and the physics of growth, had independently recreated the same type of filamentary structure that gravity and dark matter had built across billions of light years. The result was not a coincidence. Both the slime mold and the cosmic web are solving the same fundamental geometric problem: how to connect a set of points in three-dimensional space with a network of filaments that is efficient, connected, and structured. The underlying mathematics is similar even though the physical scales differ by 25 orders of magnitude. The researchers even used the slime mold model to predict the locations of intergalactic gas filaments that had not yet been detected, and subsequent observations confirmed several of these predictions. It was a beautiful example of how nature reuses the same patterns at radically different scales, from the microscopic to the cosmological. In 2005, a team of scientists at the Max Planck Institute for Astrophysics in Germany completed one of the most ambitious computational projects in the history of science, using the Regatta supercomputer at the computing center of the Max Planck Society. They simulated the evolution of the entire universe from shortly after the Big Bang to the present day, tracking the gravitational interactions of over 10 billion particles of dark matter in a cube of space, roughly 2.3 billion light years on a side. They called it the Millennium Simulation. And when they visualized the results, the image that emerged was breathtaking. A vast network of luminous filaments wove through the darkness, connecting dense knots of matter at their intersections, surrounding enormous empty voids. The pattern was unmistakable. The simulation had produced a cosmic web, and it looked almost exactly like the one that astronomers had been observing in real surveys of the sky. The numbers behind the Millennium Simulation are staggering. It tracked more than 10 billion particles, each representing a chunk of dark matter, roughly 1 billion times the mass of the Sun. The simulation volume spanned over 2 billion light years on a side. The calculation required 28 days of continuous computation on 512 processors, generating 25 terabytes of raw data. And it succeeded brilliantly. When astronomers compared the statistical properties of the simulated cosmic web to those of observed galaxy surveys, the match was remarkable. The distribution of filament lengths, the sizes of voids, the masses of clusters, the correlation functions of galaxy clustering, all of them agreed with observations to a degree that validated the cold dark matter model as a powerful, predictive framework for understanding cosmic structure. But the Millennium Simulation had a significant limitation. It tracked only dark matter. It did not simulate the gas, the star formation, the black holes, or the complex feedback processes that shape the properties of the galaxies embedded within the web. Dark matter provides the gravitational scaffolding, but the visible universe, the part we actually observe with telescopes, is made of ordinary baryonic matter. Protons, neutrons, electrons, photons, neutrinos, modeling how this ordinary matter behaves within the dark matter framework, requires simulating an extraordinary range of physical processes. From the cooling of gas in galactic halos to the explosive feedback from supernovae to the relativistic jets launched by supermassive black holes consuming material at the centers of galaxies. These processes span many orders of magnitude in scale, from parsecs to megaparsecs, and they interact with each other in complex, nonlinear ways that cannot be solved analytically. They must be computed. The Millennium Simulation was a triumph of computational cosmology. It demonstrated that the cold dark matter model, starting from the tiny density fluctuations observed in the cosmic microwave background, could reproduce the large-scale structure of the universe with remarkable fidelity. The filaments were the right length. The clusters were the right mass. The voids were the right size. The statistics of galaxy clustering matched observations to a degree that would have seemed impossible just a few decades earlier. But the Millennium simulation was only the beginning. The challenge was that the Millennium simulation tracked only dark matter. It did not simulate gas, star formation, black holes, or the complex feedback processes that determine the properties of actual galaxies. Dark matter provides the scaffolding, but the physics that determines what galaxies look like, how many stars they form, how bright they are, how they evolve, and how they eventually die involves ordinary matter, gas cooling, collapsing, forming stars, being heated by supernovae, being blasted by jets from supermassive black holes. These processes are ferociously complicated, and simulating them requires far more computational power than tracking gravity alone. The solution came with the next generation of simulations. In 2014, the Illustris project, led by Mark Vogelsberger at MIT and Volker Springel at the Max Planck Institute, produced the first large-scale cosmological simulation that included a comprehensive treatment of baryonic physics, gas dynamics, star formation, stellar feedback, black hole growth, and the energetic outflows driven by active galactic nuclei. The simulation tracked the evolution of a cube of space, roughly 350 million light-years on a side, from shortly after the Big Bang to the present, producing thousands of galaxies with a wide range of masses, shapes, star formation rates, and colors. The results were stunning. For the first time, a simulation had produced galaxies that looked like real galaxies. Spirals with delicate arms, ellipticals with smooth, featureless profiles, dwarf galaxies scattered through the voids, galaxy clusters glowing with hot X-ray gas, and all of them embedded within a cosmic web of filaments and voids that matched the observed structure of the actual universe. The Illustris simulation ran on the Curie supercomputer in France and the SuperMUC supercomputer in Germany, consuming roughly 19 million processor hours. It produced over 230 terabytes of data and tracked the formation and evolution of more than 41,000 galaxies within its simulated volume. The images it generated were so visually striking that they appeared on the cover of Nature and generated worldwide media coverage. For the first time, the public could see what a computational model of the universe actually looked like, and the resemblance to the real thing was uncanny. The successor to Illustris, called Illustris TNG, for the next generation, pushed the boundaries even further. The project consisted of 3 flagship simulations at different volumes and resolutions: TN G50, TN GON 100, and TN G300. The largest of these, TN G300, simulated a cube roughly 1 billion light-years on a side. The most detailed, TN G50, achieved resolutions fine enough to track the internal structure of individual galaxies, their magnetic fields, the flows of gas through their disks, the birth and death of stars, the growth of supermassive black holes at their centers. Illustris TNG ran on some of the most powerful supercomputers in the world, consuming tens of millions of processor hours. The TN G50 simulation alone took 26 months to complete on the Hazel Hen supercomputer at the High Performance Computing Center in Stuttgart, Germany. The total data output of the project exceeds 750 terabytes. What these simulations have revealed is remarkable. They show how the cosmic web evolves over time, how filaments thicken and fragment into galaxy groups, how clusters grow through mergers at the densest nodes, how gas flows along filaments into the hearts of galaxies, feeding the formation of new stars. They show how galaxies are shaped by their environment. Galaxies in clusters tend to be red, old, and quenched of star formation, while galaxies in filaments and voids tend to be bluer and more actively forming stars. The simulations also revealed something unexpected and beautiful. The cosmic web is not just a static scaffolding. It is a dynamic, evolving system. Gas streams along filaments like water flowing through rivers. Galaxies migrate along filaments toward clusters, spiraling inward under gravity. Clusters collide and merge in some of the most energetic events in the universe since the Big Bang, and all the while, the expansion of the universe stretches the web, thinning the filaments, expanding the voids, and gradually isolating the densest structures from one another. In a sense, the cosmic web is alive, not biologically, of course, but dynamically. It is always changing, always growing, always being reshaped by the interplay of gravity and expansion. The simulations have given us a time-lapse movie of this evolution. They show us a universe that begins almost perfectly smooth, with only the faintest whisper of structure, and gradually develops into the intricate, foam-like pattern we observe today. They show us how the first galaxies formed in the densest knots of the young cosmic web, how those galaxies grew through mergers and gas accretion, how they transformed from chaotic, irregular blobs into the elegant spirals and stately ellipticals we see in the modern universe. They show us how the intergalactic medium, the gas that pervades the filaments, serves as both a reservoir and a highway, storing enormous quantities of baryonic matter that has never been incorporated into galaxies, and channeling fresh gas from the voids into the hearts of galaxies, where it fuels new generations of stars. One of the most striking findings from these simulations is the degree to which a galaxy's fate depends on its position within the cosmic web. Galaxies that live in dense cluster environments tend to be red, elliptical, and devoid of new star formation. Their gas has been stripped away by the hot intracluster medium, or heated to the point where it can no longer cool and collapse. Galaxies in filaments tend to be in a transitional state. Some are still forming stars, others are beginning to quench. And galaxies in voids tend to be blue, gas-rich, and actively forming stars, unperturbed by the gravitational harassment and ram pressure stripping that galaxies in denser environments endure. The cosmic web is not just a backdrop. It is an active participant in the evolution of galaxies. It shapes them, feeds them, and eventually starves them. Understanding the web is not optional for understanding galaxies. It is essential, and it is that second force, expansion, that introduces the final and perhaps most unsettling ingredient in our story. In 1998, two independent teams of astronomers made a discovery that turned cosmology upside down. They were studying a particular type of stellar explosion called a Type 1a supernova. These supernovae occur when a white dwarf star, the collapsed remnant of a sun-like star, accumulates enough matter from a companion to cross a critical mass threshold and detonate in a thermonuclear explosion, because the physics of this detonation is consistent from one event to the next. Type 1A supernovae all reach roughly the same peak brightness, making them excellent standard candles, objects whose true luminosity is known, allowing their distance to be calculated from how bright they appear by measuring both the distances and the redshifts of dozens of distant Type 1A supernovae. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the Heisey Supernova Search Team, led by Brian Schmidt and Adam Rees, expected to measure how much the expansion of the universe had slowed down since the Big Bang. Gravity, after all, pulls matter together. It should act as a cosmic brake, decelerating the expansion over time. But that is not what they found. The distant supernovae were dimmer than expected, meaning they were farther away than they should have been if the expansion were decelerating. The inescapable conclusion: the expansion of the universe was not slowing down, it was speeding up. The discovery was shocking. It contradicted the most basic expectation of a universe filled with matter. Gravity should slow down expansion, not accelerate it. Something else, something with a repulsive gravitational effect, had to be at work. The two team leaders, Saul Perlmutter, Brian Schmidt, and Adam Rees, Schmidt and Rees leading the Heisey team together, would eventually share the 2011 Nobel Prize in Physics for this discovery, which has been called one of the most important in the history of science. Something was pushing the universe apart, overcoming the gravitational attraction of all the matter in the cosmos. Something with an energy density sufficient to dominate the large-scale dynamics of the universe. Something that constituted roughly 68% of the total energy content of the cosmos. When combined with the roughly 27% contributed by dark matter, and the mere 5% contributed by ordinary baryonic matter, the composition of the universe was suddenly revealed to be far stranger than anyone had imagined. We are made of the minority ingredient. The universe is ruled by forces and substances that we cannot see, cannot touch, and cannot yet explain. They called it dark energy, and more than a quarter of a century later, we still do not know what it is. The simplest model for dark energy is Einstein's cosmological constant, a constant energy density pervading all of space, unchanging over time. In this model, dark energy is a property of empty space itself. Every cubic meter of vacuum contains a fixed amount of energy. And as the universe expands and the density of matter drops, dark energy's contribution becomes increasingly dominant. In the current epoch, dark energy has already won. The expansion of the universe is accelerating, and that acceleration is increasing over time. Einstein himself had a complicated relationship with the cosmological constant. He originally introduced it in 1917 as a fudge factor to keep the universe static, before Hubble's discovery of the expanding universe rendered it unnecessary. Einstein reportedly called the cosmological constant his greatest blunder. But nature, it turns out, had the last laugh. The cosmological constant, or something very much like it, appears to be real. The irony is exquisite. The thing Einstein added to his equations to prevent the universe from moving turned out to be the thing that is making it move faster and faster. The physics behind dark energy is deeply mysterious. If the cosmological constant is caused by the energy of the quantum vacuum, the sum of all the zero-point energies of quantum fields, then quantum field theory predicts a value that is roughly 120 orders of magnitude larger than what is observed. This is often called the worst prediction in the history of physics, and it suggests that our understanding of the connection between quantum mechanics and gravity is profoundly incomplete. For the cosmic web, the implications are profound. In the early universe, gravity was the dominant force on large scales. Matter collapsed into filaments and clusters. The web grew denser and more structured over time. But as dark energy gained the upper hand, the balance began to shift. Expansion started to outpace gravitational attraction on the largest scales. Structures that were already gravitationally bound, like galaxy clusters, remained intact. Their internal gravity was strong enough to resist the outward push of expansion. But the filaments connecting them began to thin. The voids began to expand more rapidly, and structures that were not quite dense enough to be gravitationally bound, like the superclusters defined by Tully's watershed analysis, began to drift apart, their member galaxies slowly separating as the space between them grew. This is the great irony of the cosmic web. Gravity spent billions of years building it, painstakingly assembling matter into filaments and clusters and walls. And now dark energy is slowly dismantling it, stretching the filaments, expanding the voids, and isolating the densest structures from one another. In the far future, if dark energy continues at its current strength, the cosmic web will be shredded. Filaments will dissolve. Superclusters will fly apart. Galaxy groups that are not tightly bound by gravity will disperse. Eventually, trillions of years from now, each gravitationally bound cluster of galaxies will become an isolated island, surrounded by an ever-expanding ocean of empty space. The filaments that once connected them will have thinned to nothing. The voids will have expanded beyond comprehension. An astronomer living in that distant era, looking out from a galaxy within a lonely cluster, would see nothing at all beyond the boundaries of their own gravitational island. The rest of the universe would have receded beyond the cosmic horizon, its light redshifted to wavelengths longer than the observable universe. The cosmic web, the largest structure ever to exist, will unravel, and all evidence that it ever existed will be erased. But there is a twist. The latest results from the Dark Energy Spectroscopic Instrument, or DESI, suggest that dark energy may not be constant after all. DESI is one of the most ambitious astronomical surveys ever undertaken. Mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, it uses an array of 5,000 robotic fiber optic positioners to capture the spectra of thousands of galaxies and quasars simultaneously. Its goal is to create the largest three-dimensional map of the universe ever made, covering over 14 million galaxies and quasars, and spanning 11 billion years of cosmic history. DESI measures the baryon acoustic oscillation signal at many different cosmic epochs, tracing the expansion history of the universe with unprecedented precision. Since beginning its survey in 2021, DESI has observed a new set of up to 5,000 galaxies every 20 minutes, often capturing spectra for more than 100,000 galaxies in a single night. It is building a three-dimensional map of the universe that stretches back 11 billion years, with a precision better than 1% in its expansion history measurements. And in its first-year results, released in 2024, and especially in its more robust three-year results, presented in March of 2025, DAISY found something unexpected. The data, when combined with measurements of the cosmic microwave background and observations of supernovae and weak gravitational lensing, favored a model in which dark energy is not constant. It appeared to be weakening over time. The statistical significance of this result reached as high as 4.2 sigma, depending on which datasets were combined, approaching the 5 sigma threshold typically required for a discovery in physics. If dark energy is dynamical, if its strength changes over time, then the fate of the cosmic web is far more uncertain than we thought. A weakening dark energy might mean that the expansion eventually slows. In the most extreme scenarios, the universe could someday stop expanding altogether and begin to recollapse. In a reversal of the Big Bang, sometimes called a big crunch, though this remains speculative, it is a possibility that just a few years ago, most cosmologists had dismissed as essentially ruled out. Meanwhile, the European Space Agency's Euclid Space Telescope, launched in July of 2023, is beginning to provide its own independent measurements. Euclid is designed to map the shapes and positions of billions of galaxies using weak gravitational lensing. The subtle distortion of distant galaxy images by foreground dark matter and galaxy clustering to trace the distribution of dark matter and the influence of dark energy across cosmic time. The telescope orbits the Sun at the second Lagrange point, 1.5 million kilometers from Earth, where it has a clear, unobstructed view of deep space. Its survey will eventually cover roughly a third of the sky. In March of 2025, Euclid released its first tranche of data, known as Quick Release 1 or CONE. Observations of 26 million galaxies across 63 square degrees of sky. The data revealed the unprecedented power of the telescope, with images sharp enough to resolve the detailed structure of galaxies across billions of light years. The CONE release included a striking recreation of the classical Hubble tuning fork diagram of galaxy morphology, constructed entirely from Euclid imaging data, showcasing the wide range of galaxy shapes, from grand design spirals to smooth ellipticals, captured in the survey's early observations. In the coming years, as both DAISY and Euclid accumulate more data, the two experiments will provide complementary and overlapping measurements that together should either confirm or refute the hint of dynamical dark energy. DAISY measures the expansion history through spectroscopic galaxy redshifts. Euclid measures the growth of cosmic structure through the shapes and clustering of galaxies. Taken together, they probe the universe from two independent angles, making their combined conclusions far more powerful than either alone. Together, DAISY and Euclid represent a new era in our exploration of the cosmic web. They are not just mapping where galaxies are. They are measuring the forces that shape the web, testing the laws of gravity at cosmic scales, and probing the nature of the two most mysterious substances in the universe, dark matter and dark energy. The cosmic web, which began as a puzzle in a redshift survey from the 1980s, has become one of the most powerful tools in all of physics. Let us return one final time to where we began. To you, to this moment, to the simple act of looking up at the night sky and wondering what is out there. You are made of atoms that were forged in the cores of ancient stars. Those stars formed in galaxies that condensed from gas that flowed along filaments of the cosmic web. Those filaments were sculpted by dark matter that began clumping in the very first moments after the Big Bang, following a blueprint inscribed by quantum fluctuations during inflation. The fluctuations that created your corner of the universe were imprinted less than a trillionth of a second after the cosmos was born. The chain of causation is unbroken. The quantum fluctuation that became the density perturbation, that became the dark matter halo, that became the filament, that became the galaxy, that became the molecular cloud, that became the star that forged the carbon in your bones. Every link in that chain can be traced. Every step can be modeled. Every connection can be measured. You are not separate from the cosmic web. You are a product of it, a consequence of it, an expression of it. And yet, here is the thing that never ceases to amaze me. The cosmic web does not know you are here. It has no awareness of itself. It is a pattern assembled by gravity from quantum noise, stretched across billions of light years, containing trillions of galaxies and quintillions of stars. And on one of those stars, on one small rocky planet in the outer suburbs of one unremarkable spiral galaxy, near the edge of one modest supercluster, matter has organized itself into a form that can look back at the web and understand it, that can map it, simulate it, name it. We are the universe studying itself, and the cosmic web is the largest object we have ever studied. The surveys are getting bigger. The simulations are getting more detailed. The telescopes are getting more sensitive. Within the next decade, instruments like Daisy, Euclid, the Vera C. Rubin Observatory, with its legacy survey of space and time, and the Square Kilometer Array will map the cosmic web in 3 dimensions with a precision that would have seemed like science fiction even 20 years ago. The Vera Rubin Observatory alone, named after the astronomer, whose rotation curve measurements helped confirm the existence of dark matter, will survey the entire visible southern sky every few nights, detecting tens of billions of galaxies, and creating a motion picture of cosmic structure evolving in real time. The Square Kilometer Array, a radio telescope spread across 2 continents, will detect the faint hydrogen gas that pervades the filaments of the cosmic web, mapping the invisible scaffolding that supports the galaxies we can see. Together, these instruments will measure the properties of dark matter and dark energy, test our theories of gravity at the largest scales imaginable, and probe the fundamental physics encoded in the structure of the web. They will look back in time to epochs when the web was still young, when the first filaments were just beginning to form, when the universe was a fraction of its current age. And they may, just perhaps, reveal something entirely unexpected, because if the history of cosmology teaches us anything, it is this: the universe is always bigger, stranger, and more beautiful than we imagine. Every time we thought we had found the edge, we discovered there was more. Every time we thought the pattern was random, we found structure. Every time we thought we understood, the universe gently reminded us that we had only scratched the surface. We once thought the Milky Way was the entire universe. We were wrong. We once thought galaxies were distributed randomly through space. We were wrong. We once thought the expansion of the universe was slowing down. We were wrong. We once thought dark energy was a simple constant. We may be wrong about that too. The cosmic web stretches across billions of light years, connecting trillions of galaxies, woven from dark matter and light, and the frozen echoes of sound waves that rang through the universe when it was less than 400,000 years old. It is the largest, most intricate, most beautiful structure that has ever existed, and we live inside it. Look up tonight. If you are far enough from the city, you will see the Milky Way stretched across the sky, a pale band of ancient starlight. Every one of those stars is embedded within a galaxy, and that galaxy is embedded within a filament, and that filament is connected to a node, and that node is connected to a wall, and that wall borders a void. And together, all of it, from the smallest dwarf galaxy to the most enormous supervoid, forms the cosmic web. You are sitting in it right now. You are breathing atoms that were once adrift in its filaments. You are held together by forces that obey the same laws that built it. And you are reading these words on a planet that exists because 13.8 billion years ago, a quantum fluctuation in the first instant of creation made one patch of space ever so slightly denser than its neighbors. That is all it took. One fluctuation, one tiny seed, and from it, everything grew. You are part of something extraordinary, something that began in the first fraction of a second and will endure in one form or another for as long as the universe itself persists. The cosmic web is the story of the universe, and it is far from over. You have been watching the entire history of the universe. Do not forget to like and subscribe, and leave us a comment to tell us what you think. Thanks for watching, and we will see you next time.